Vladimir Dokchitser from Cambridge, and he will speak on the parity of ranks of elliptic curves.
Thanks. So first of all, I'd like to thank the organizers for giving me the opportunity to speak here. So I will indeed talk about parity of ranks of elliptic curves, and my elliptic curves, they're going to live over number fields. So E is going to be always an elliptic curve, and it's going to live over K, which is going to be a number field. And I should say that really at the back of my mind, I do have something as elementary as looking at the solutions to a Diophantine equation of this kind. So let me just remind you that the solutions to this equation, if you chuck in the point of infinity, they form an abelian group. And the crucial fact about it is that that thing is finitely generated. So it's a finite group, finite abelian group, times a bunch of copies of Z. And this number of copies, which somehow measures just how infinite your solution set is what we call the rank of the elliptic curve. So I will talk about the parity of this thing. The rank itself is pretty much impossible to compute, even if you allow yourself to use any conjectures you like. Well, if you're over Q, you can try to use the Birch-Swinton Dyer conjecture, but even computing the order of vanishing of the L function at s equals 1 is a bit of a headache to actually prove that it has the order of vanishing you think. And if instead you try to do, say, 2 descent, well, you get into this problem about the Tate-Shafarevich group being non-trivial, so you're going to get a headache as well. But if you just want the parity, it turns out that life is much, much better. So let me say that we expect the parity of the rank to be given simply by a sum of purely local invariants. So if you want to formalize that a bit, what I mean is what we have is some invariant, let me call it M, of elliptic curves over local fields so that the rank mod, sorry, that's mod 2, is given by the sum of these local invariants of the elliptic curve over the local fields, the sum being taken over all places. And of course, we'd like this sum to make sense. So here, these local terms, they should take the values plus minus 1, sorry, 0 or 1, and equals 0 for almost all v. So what I'll basically discuss today is where this comes from. It's somehow a standard consequence of the Birch-Swinton Dyer conjecture, but I'll also explain that it also follows from finiteness of the Tate-Shafarevich group, well, which is again, of course, conjectural. And then I'll try to explain some of the arithmetic consequences of having such a formula here. So a lot of what I say today is just well-known standard facts about the consequences of the Birch-Swinton Dyer conjecture, but I'll also say some other things which are joint work with my brother. Right, so to begin with, maybe I should just remind you about the Birch-Swinton Dyer conjecture. for elliptic curves over number fields. We could do for abelian varieties. And in fact, a lot of what I say is true about abelian varieties, but I'd like to keep things a bit more straightforward. So this has two parts. Let me just, for the moment, remind you about the first part. So what it says is that if you look at your elliptic curve, then you can read off its rank from its L function. Of course, for a general number field K, we don't know the L function to be even well defined at s equals 1. So it's somehow, there are some conjectures even before you can state this that go into it. So why does that help with parity? Well, okay, so this would be B as D implies parity formula. Well, the reason is that the parity of this object is quite easy to compute because you have the functional equation for the L function, which says that the L function at S is, well, I won't throw in the precise gamma factors and the exponential factor, but roughly speaking, it's the same as the L function at 2 minus s. So this point s equals 1 is at the center of symmetry of the L function. And in here you have a sign. It's either plus or minus. So if you were working with Dedekind zeta functions, you'd always have a plus, but in case of elliptic curves or abelian varieties, you have sort of two cases. Now this sign is what we call the global root number, and I'll denote it by W. And the sign being plus means that basically your function is even around s equals 1. So if you sort of imagine a graph, sort of go like that, or if the sign is minus, it might go like that. But so that means that the sign will determine the order of vanishing at s equals 1, depending on whether it's plus or minus. So the order of vanishing of the L function at s equals 1 is going to be even or odd, depending on whether the root number is plus 1 or minus 1. Now, of course, I haven't yet told you what the root number is, so at the moment this is just an abstract object, but somehow the general formalism for L functions tells you that this global root number is, well, it's defined, in fact, to be a product of local root numbers which are purely local invariants. So in other words, the sign in the functional equation is governed by local data, and therefore, if you invoke the Birch-Swinton-Dyer conjecture, you obtain that the rank of the elliptic curve is indeed governed by local data. So we can take our local invariant M to be 0 or 1, depending on what the local root number is. I should sort of say, of course, I haven't defined local root numbers for you either. I've just sort of pulled this formula out of nowhere, and I'm not planning to define it because the definition is quite complicated. Again, this bit you can replace E by A and make it into an abelian variety. That works perfectly well. The good thing with the elliptic curves case is that these local root numbers, they've been classified, so if you actually have an explicit elliptic curve, you can compute these things. So there exists a classification for these features. And let me just tell you what it is in simple cases. So if, well, okay, for completeness, I'll need to tell you about the Archimedean case. So there the local root number is always -1. In other words, if you want to compute the parity of the rank, you have to count the number of infinite places. Not very hard, but they do make a difference. If your elliptic curve has good reduction, you can just ignore it. So in other words, the root number is +1. Which is sort of good news because it means that that infinite product defining the global root number, it actually makes sense. There are only finitely many places that contribute. If the curve has multiplicative reduction, well, then it depends whether it's split multiplicative or non-split. So if it's split multiplicative, then the root number is -1. And if it's non-split, then the root number is +1. If you have additive reduction, well, then there are basically many, many more cases to consider. So I won't write them down. So there are formulae, most of them, so somehow the main chunk is due to Rolich. So he did all the cases when your residual characteristic is at least 5, and the cases of residual characteristic 2 and 3 are total nightmares. Kobayashi did residual characteristic 3, and residual characteristic 2 was done by David Whitehouse and me and Tim sort of separately. But in any case, somehow ignoring additive reduction, let's say you have a semi-stable elliptic curve, well, you can read off the parity of its rank, right? You compute the number of infinite places, you compute the number of places of split multiplicative reduction, and you know the parity of the rank of the elliptic curve.
I'm sorry, could I ask about that? What you were saying just now, when you say these formulas were due to these people, you're speaking about a specific formula, or I'm not sure.
So let's say it's formulae of these kind. So take an elliptic curve of a local field if it has reduction type 3 star and
some specific collection of formulas.
Yeah, it's some very specific collection of formulas.
I mean, even the definition is in principle computable.
Not really. Well, it depends what you mean by computable. You have to be able to somehow work out what your Tate module looks like. You have to do explicit induction of to reduce to one-dimensional characters, and then you actually have to compute those creatures. So, yeah, if you want to do it in practice, you do need
some formulas.
You need some formula, absolutely. Right, but let me sort of come back to this business about the rank being a sum of local terms. So, well, this is an explanation of why that's true, but of course this is a bit of a cheat, because what we've done is said, right, first of all, we're going to use the Birch-Swinson die conjecture, but even after that, we said, well, the L function test equals 1 might not make sense, but we are going to define the parity of the order of vanishing to be whatever we get from the sign in the functional equation. And we're going to define the sign in the functional equation to be a product of local terms. So we basically said, right, we're going to define the parity of the order of vanishing to be given as a sum of local data. That doesn't exactly explain why something like this might be true, but it is certainly a consequence of the Birch-Swinton-Dyer conjecture. So if you do regard it as a bit of a cheat, let me give an alternative explanation, which is somehow more arithmetic in nature, doesn't use L functions. So this will be again, I definitely need to use a conjecture. We certainly have no idea how to prove this sort of statement unconjecturally. But this time I'll be using finiteness of the Tate-Shafarevich group. So I said I won't use L functions, but let me just turn to L functions just for a second, because they're really the motivating object still. So let me remind you of the second part of the Birch-Swinton-Dyer conjecture. So what it says is that if you look at your L function, and if you look at the leading term in the Taylor expansion at s equals 1, so if your rank is 0, this would be just the value. Otherwise, it's the first non-vanishing derivative, suitably normalized. Then, well, you have an explicit formula for this thing. So let's see, you need the regulator of the elliptic curve, you need the size of its Tate-Shafarevich group, you need product, the Tamagawa numbers and the periods. I'll just denote them by capital C. And you divide it by the square root of the discriminant of the number field and the size of the torsion squared. So this C is the product of periods and, as it were, local fudge factors in the formula. Let me not sort of go into details here. What matters for me is that this is a product of local data. Well, it's almost true. There's sort of, strictly speaking, one small technical detail, but I'd like to brush it under the carpet, at least for the moment. So if K is Q, then this is just the good old real period, omega plus, and the Tamagawa numbers, CP. But so far as this talk is concerned, this is product of local terms. Right, so let me try and explain what happens somehow in this arithmetic setting. So the thing that we can prove, so I'll use the multiplicative notation here, is the following. Suppose we have an elliptic curve over any number field. And so what I'll need to assume is this business about sha being finite, and I'll need it over a slightly bigger field, unfortunately. So the field I need is where we have adjoined the two torsion points of the elliptic curve to the ground field. In this case, the rank of the elliptic curve can be read off from these products of local terms, as it were. So, well, let me give you an explicit formula. I'll explain the notation in a moment. So in this expression here, the curve E dash that comes in is some curve 2 isogenous to E. And the field L is the field where you obtain this 2 isogeny. And somehow to get this formula to a finite length on the blackboard, I actually had to take a slightly more careful choice. If the elliptic curve of a K already has a 2 isogeny, then we must take that one. And K square root of delta E, so delta E is the discriminant of the elliptic curve, but that's the quadratic extension inside the 2 torsion extension for E.
Taking the three-adic order of a square on the...
Ah, that's an optical illusion.
Oh, okay.
The point is, I have these periods, which are horrible transcendental things. So when you square them, and
there's some cancellate.
there's some
C over F isn't algebraic.
Hmm?
C over F isn't an algebraic number.
Yeah, it isn't. So these quotients turn out to be rational, and then you can take this valuation. But
Gotcha.
yeah, you could suitably tweak the convention so that you can get rid of those squares, but then you probably don't want to do that actually.
Also another question, the field of definition is unique in this case?
You mean for this E prime?
Yes.
No. So sorry. So what I'm saying here is that if you do have a 2 isogeny, then you have to take that one.
You choose a field of definition.
Sorry, I'm not exactly
If
sure.
the two isogenies defined over K, then can L still be anything? Could L be
No.
N?
No. Sorry. If it's defined over,
As a field of rationality, which is unique, but is it defined over it?
But a point of order 2, a group of order 2 will be defined over L if and only if the non-trivial element's defined over L.
yeah, you have a very small group. There's somehow. So, actually, let me perhaps elaborate a little bit on that. So, if you look at that result there, it doesn't quite tell you that this rank mod 2 is a sum of local invariants. So these objects are products of local terms, so that when you take two-adic valuation, it is basically a sum of local invariants. But you do indeed have this field varying, and it's varying globally. Right? So I haven't really expressed it in the fashion that I promised. And secondly, that there is this two-isogenous curve, which again I have picked globally. So again, there is a bit of a headache that it's not quite honest if I want to really write it as a sum of local terms. But let me sort of just put in brackets that plus a bit more work that will give you a local formula. So the local expression you're going to get is very unpleasant. You sort of have to symmetrize with respect to these two isogenies so that the object you get in the end is indeed perfectly well defined. But somehow I just like to brush that under the carpet and pretend that that problem isn't there. I'd like to just very briefly sketch where this result comes from. So I'll do it sort of case by case according to what your two torsion looks like. So, generally speaking, you join the two torsion of an elliptic curve to the field K. The Galois group is at worst S3 because the two torsion, so if you remember the equation I wrote down in the beginning, the two torsion points are just classified by the roots of this cubic. They're going, so y coordinate 0, x coordinate a root of the cubic. And the Galois group of that creature is certainly at worst S3. So in the case when the Galois group is either trivial or C1, sorry, or C2, then in other words we are saying that the elliptic curve has got a two torsion point. And so we have a k-rational isogeny. And our field L is just the base field K itself. And we're trying to prove the formula on the very, very top of that board. So actually do this on the overhead. So this computation, which as far as I know was first done by Birch. So suppose you do have an elliptic curve which has a 2 isogeny. Well, then the L functions of E and E prime are the same, because their Tate modules are isomorphic after you tensor them with Q. And Castles proved that the Birch-Swinton-Dyer conjecture is compatible with isogenies. So we just invoke that. Then we stare at this horrible formula, the Birch-Swinton-Dyer quotient for E and the Birch-Swinton-Dyer quotient for E prime. And well, basically what we do is try to construct a counterexample to it. The difficulty with doing that is that there are a few terms that you have no control over. More precisely, the Tate-Schaferevich group is absolutely impossible. But we do know one thing about the Tate-Schaferevich group. If it's finite, then its order is a square. So what you do is say, right, I'm going to work up to squares. And quite a few things go away. So the torsion squared goes away, Shah goes away. Well, the square root of the discriminant, of course, goes away even without that. And then you have an expression relating these local terms to the regulators. So if the rank was 0, then the regulators are trivial, they're just 1. What you're saying, for instance, is that this quotient of local terms has to be a perfect square. Even that is actually a non-trivial statement, because it tells you that local data is somehow linked to the fact that the regulators are trivial to global objects. So if you want to do the computation of regulators in general, well, you just do it basically. Pick a basis for the points of infinite order on E. Pick a basis for the points of infinite order on E prime. Look at the image of the EI in E prime. That's going to give you a lattice of finite index. I'll just call this index n. And now compute the regulator. So by definition, it's the determinant of the height pairing computed on the E primes. Now, if we replace the E primes by the phi of EIs, we're going to get a factor of n squared out, because we have a symmetric bilinear pairing and we are taking index n sublattice. The n squared, of course, is not going to matter because we work up to squares in the end. Now, that you can rewrite as the determinant of EI comma phi star phi. So phi star is the adjoint isogeny, the dual isogeny to phi. When you compose phi star with phi, you get a multiplication by 2 map. And that, in turn, is now essentially the regulator of E, except that you are out by a factor of 2 to the r, where r is the rank of the elliptic curve. It's the dimension of this vector space spanned by the EIs. So putting all that together, what we've just shown is that the parity of the rank of the elliptic curve in this case can be indeed read off from these local terms CE, which is exactly the formula I promised in the case when you do have a 2 isogeny. So somehow so in other words, what we do is we invoke invariance of BSD under isogeny look at the resulting formula mod squares to eliminate SHA. And make a simple regulator computation to deduce that the parity of the rank can be read off from these local terms, from the Birch-Swinton Dyer-Fudge factors. Well, and let me just very briefly sketch the other cases. If you don't have a 2 isogeny, but the Galois group is still not the full group, but just cyclic of order 3, so in this case, your field of definition of the isogeny is going to be the full 2 torsion field. Well, then actually nothing really happens. The rank of the elliptic curve over K mod 2 is the same thing as the rank over the C3 extension, because you're going up a cyclic extension of odd degree. The parity of the rank can't change. So let me just say this is an exercise in elementary representation theory. And now we can invoke the first case. Over the top field. So this is some of the C3 cases, just an elementary consequence of Birch's result.
Sorry, can you give me an example of Galois group in C3?
Well, to get C3, all you need is the discriminant of the elliptic curve to be a perfect square. So if you like, take any elliptic curve, adjoin the square root of the discriminant to your number field, and then at least provided your elliptic curve is sufficiently generic, you're going to get just C3. Now the last case, somehow the general one, does require an extra ingredient. So this is going to be the non-abelian part of this talk. And actually the ingredient I need can be done for quite general, well, for general, I should say, Galois groups. But I'll just stick to C3 because that's the only one I need. And again, I'm just going to do a very rough sketch. So, what you cook up is you take, so let me remind you, in this setting, we have S3 here, C2 here, and C3 here. So you cook up a couple of abelian varieties which are isogynous. So you take the Weil restriction from F down to K of, so you base change your elliptic curve to F and then Weil restrict it down to K. Oh, thank you. So that you get a 6-dimensional abelian variety. Add to it a couple of copies of E itself. This thing is then isogynous to a couple of other way restrictions. So we restrict to L twice, from L twice, and once from K root delta E. So another 8-dimensional abelian variety. The fact that they're isogenous is just some representation theoretic consequence. You can construct these kinds of relations in large quantities whenever you have a non-cyclic Galois group lying about. Now that you have two isogenous objects, you just follow the same path as before. Use invariance of Birch-Swinton die and isogeny. This time for abelian varieties. So proved by Tate and Milne.
What's the degree of this isogeny?
Well, you have lots of isogenies, strictly speaking. It depends which one you choose. So the sensible one, it's some power of 3. But I don't quite remember which one, to be honest. Okay, so you, again, so when you have two isogenous abelian varieties, the L functions are the same. You say the Birch-Swinton die quotients are the same. Compare the two, like we did there, and throw away all squares. So you get a formula involving regulators and these computable local terms for the elliptic curve over the various fields. Make a regulator computation, this time using the fact that the height pairing is Galois invariant, to deduce that, so let me just try to get this right, the following combination of ranks can be read off from local data. So in other words, the sum of the ranks over K plus L plus F is computable using local data. Over L we have a 2 isogeny to play with, over F we have a 2 isogeny to play with, so those two ranks we can control already, so we are done. And that's how you get the rank formula in the S3 case.
Lad, is that the only place you're going to use finiteness of Sharp
Yes.
to get this equation?
Well,
Is there any hope of proving that equation without finiteness of Sharp? Because it's Sharp independent.
yes,
It's hence ratio of regulators is ratio of students.
it would be good, but I'm afraid that's far too optimistic. But it's true. We're relating two totally elementary invariants, the rank and local things, but not the slightest idea how to get rid of the Sharp contribution. So we use finiteness of Sharp to use the isogeny case, and of course this S3 case as well, where we use finiteness of Sharp for all these abelian varieties in the middle.
What if you just knew the two finiteness of Shah?
Right, so to be more precise, I just erased the statement of the theorem. We actually used,
6 finiteness.
yeah,
2 or 3.
but unfortunately over the stop field F. So, right, but anyway, to forget about this for a moment, let me come back to where I started. The rank of an elliptic curve over a number field is a sum of local invariants. So I've explained why this is predicted by the Birch-Swinton-Dyer conjecture, and somehow showed that it's also predicted by finiteness of the Tate-Shaffer-Average group by cooking up a formula in each case. There's sort of a natural question: are the two formulae actually compatible? It would be very interesting if they weren't. But yeah, they certainly are. So in other words, that creature there is going to be congruent to 0 or 1, depending on the root number. Now, morally, this is a purely local computation. After all, we've expressed, so the root number is given as a product of local root numbers. That object there is basically a sum of local terms, so we just need to compare each term locally. There is a little problem, is that they don't actually agree locally. They only agree after you've taken the product of all places, because there's some very, very annoying correction term that you have to identify.
Without any hypothesis?
Yeah, so, but this is without any hypothesis, yeah. So, non-conjecturally. So for this, we don't need finiteness of Shah, anything like that.
Sorry, and K is arbitrary, right?
Arbitrary number field, yeah. So if we were working over Q, we'd have lots and lots of things we could use, like modularity, Gross-Zagierjang formulae of various kinds, convergence results, which somehow give a much greater supply of things we already understand. But over arbitrary number fields, we somehow don't have that luxury. Oh, and I guess I should insert a corollary here. So if the Tate-Shaffer-Average group over this slightly bigger field is finite, or indeed if its 2 and 3 primary components are finite, then the rank of the elliptic curve mod 2 is indeed what the Birch-Swinton-Dyer predicts it should be.
Is there a single elliptic curve for which one can prove that that Tate-Shaffer-Average group is finite, and for which the statement after it was not already known?
A single elliptic curve for which you can prove that Psi is finite.
I mean, if he's got all his 2 torsion, for example, and defined over Q, then Gross-Zagier or Kolyvagin or whatever, then maybe you can prove that Psi is finite. But that machine that proved it was finite would also prove that the rank was the order of magnitude of the
Yeah, because the way you prove that Psi is finite is by
Exactly.
computing the rank.
Yeah, yeah.
So it's, as far as I'm aware, no. So this can only be used for predicting things, not for actually.
But I mean, one
proving
day
things
the answer might well be yes.
Sure.
That's fine.
Or no, which would be also fun. Right, so in the remaining 10 minutes, let me just give some consequences again, I just want to return to this statement that the rank is a sum of local invariants. I basically just want to try and explain what sort of a constraint this is and what sort of things it predicts. So to begin with, let me take the extension over Q, f adjoin I square root of 17. So this is an example that I got from Carl Rubin, and which is a little bit crazy in a certain sense. So now, if you take any elliptic curve over Q, well, okay, let's look at what happens over this biquadratic field. And I'm going to use root numbers to compute the parity of the rank. So if you want to compute the root number over f, it's a product of local root numbers. These are purely local invariants, so they only depend on the field fv. Right? They don't see the global field f plus the place, they just see the local field fv. So what we can do is we can sort of pair them up according to their residue characteristic. Right, there's a product over usual primes, and then those v dividing p. So, because, as I say, these are purely local invariants, it won't matter. The local contribution from v is always the same over each prime. Each v over a given prime p gives the same contribution. And because we've carefully chosen our field so that all primes split, that means that the number of these primes is always either 2 or 4. So in total, the root number is +1, purely from the fact that it's a product of local root numbers. Right? We haven't used any explicit formula anywhere for this. So in other words, if you take any elliptic curve over Q, its rank has got to be even over this field. So, of course, this you can do this for a billion varieties equally well. So perhaps I can even rephrase that. There's no abelian variety over Q with odd rank over Qi root 17 for some absolutely obscure reason. I should sort of say that this is very much a parity phenomenon. If you, for instance, wanted to take, let's say, a bicubic extension, so Galois group C3 cross C3, where every prime splits, and then ask the question, well, is the rank always divisible by 3 in that case? After all, you do exactly the same computation. And, well, the answer is no. So you can have an elliptic curve over Q, f over Q, C3 cross C3 extension, in which all primes split, and the rank of the elliptic curve over the top field is not divisible by 3. So in other words, while the parity of the rank is a sum of local terms, the ternity, trinity, whatever it is of the rank isn't. Because if it were, you'd always have to have the rank divisible by 3 in such extensions. And you can just basically take the first elliptic curve and the first bicubic extension you find, and it just doesn't work.
I didn't quite understand. What did you say was the reason for 1, your assertion 1?
So assertion 1 is exactly that computation. you compute the root number over this biquadratic field,
Right.
you find it's always +1. So the rank has to be even.
But that's assuming conjecture.
Oh, of course, of course. Ah. Absolutely. I mean, I am assuming Birch-Swinton Dyer or fineness of Shah.
But I guess with that example, there are at least a wide class where you don't have to assume any conjecture.
Sure. Well, in the sense that you can find many examples where this is true, but somehow the crucial point is that this always has to happen.
But I mean, many examples with finiteness of Shah.
Yeah, but in those examples, I'm afraid you
Oh,
can
yeah,
compute the
you're
rank
right.
anyway.
No, fine.
Yeah.
Yeah.
So it's
That's the same remark again, yeah.
yeah. So let me now give a different example.
Sorry, so you have any other interpretation of this phenomenon? Somehow?
You mean why this should be true?
Right.
Some basic Galois theory argument?
No, definitely not. Somehow your Galois group is C2 cross C2. Why shouldn't you have just one copy of the trivial representation in the Galois group?
You somehow have to use the fact that there's no totally ramified prime or something. You know,
Total nonsense. Yeah. Yeah. It's somehow it's the local data here that's controlling it.
Oh, so maybe you can get something like this for the Selmer group. Maybe for that you there's a Galois theory.
how are you going to
Still no.
Still
No. We don't have a sufficiently good control over Selmer groups either, I'm afraid. Well, no, sorry. I mean, no, we do know that the parity of the analytic rank is compatible with the parity of the rank of the P-Selmer group over a field like Q. So for Selmer groups, you can prove something of this result, but just over base field Q, basically.
Just over base field Q, and then this what I mean is
Any suitable biquadratic
I see,
of this kind.
That seems like it should be Galois theoretic.
But no, that's not pure Galois theory. You need to use some rather horrible things for that.
What's horrible?
Well, as I say, results from modularity and so on. You have to know, you have to use the fact that the parity of the rank of the P-Selmer group is compatible with the root number, and that's not a trivial statement. So if it were sort of pure Galois theory, you could do it over any number field, and we don't know how to do that over any number field. So in the remaining minute, let me just do one more example. So let me take this elliptic curve here. So discriminant minus 11 to the power 4. It acquires, so it has potentially good reduction everywhere. In other words, at 11 because the other primes have good reduction already. And if you just brutally adjoin the 12th root of minus 11, then you get good reduction there as well. So let me just look at what happens over extensions of this field K, which is when we've already adjoined the 12th root of minus 11. So let's take any extension and compute the root number over that field. Well, all our places are complex. Their number is, well, we already have 6 of them over K, so over F we're going to have 6 times something, an even number. Bunch of contributions from finite places, but of course we have good reduction everywhere, so they don't contribute. So the global root number is again +1. In other words, the parity of the rank should always be even, no matter which field you go to. So in other words, if I give you this elliptic curve and I give you a field extension of K and tell you, you've got a point of infinite order there, you can say directly, that means there is another point of infinite order. Now I have not the slightest idea how to construct that second point of infinite order, but it should be there. And I should sort of make just a small warning. Well, if the elliptic curve had Cm, I'd know how to construct that second point of infinite order, because I could hit my point with the complex multiplication structure. This elliptic curve certainly isn't Cm. And you can also do perhaps a slightly different crazy thing. If you just looked over this degree 6 extension, q6 root of minus 11, and you were to compute the root number of field extensions of that, so you already have everywhere good reduction over that smaller field. In this case, again, finite places don't contribute. The infinite places, well, you have 3 complex places over k prime. So the total number of places you're going to get is 3 times the degree. So in other words, the parity of the rank is simply going to be given by the degree of the extension of your field f over k prime. So somehow it's a very nice and regular behavior of the parity of the rank. In particular, it means that all quadratic twists have positive rank. And so this is in contrast to what happens over Q, where you have Goldfeld's conjecture, which says over Q, if you have an elliptic curve, look at its quadratic twists, half of them have rank 0, the other half have rank 1, and the rest are sort of few and far between. In particular, it means that, so in this final example, if you have an extension of even degree, then the parity rank of the rank changes. You had odd rank, now you have even rank. So it means that you must have got a new point on the elliptic curve. In fact, you must have higher rank, but somehow, even in terms of very, very basic, of a very, very basic question, we are saying that this equation here obtains new solutions over any extension of even degree. Again, no idea how to construct them, but they somehow should be there. Right, thanks very much.
Before we go on with the questions, I think it would be fair for the people who don't read the journals to give credit to the previous proofs of the equation.
Yes. Now, there's a long list of people who did various things on parity conjectures of various kinds. So the first results I know are due to Birch and Stevens, who basically used this observation of Birch that I mentioned.
Perhaps we can limit ourselves to the parity case, parity result.
Yeah, so that's parity over Q for, let me try to remember, I think they did CM elliptic curves. But they proved a parity statement. Then there was Greenberg and Gore, who did, now let me try to remember, who also looked at CM curves, I think again over Q, and they did, so they considered Selma groups rather than just general ranks. So this is P Selma versus analytic. And I guess they needed P ordinary. And then Monsky, he proved the parity conjecture that, in other words, the parity version of the Birch-Van-Dijk conjecture for elliptic curves over Q, assuming finiteness of Shah. And of course, there's the famous work of Nekavard, So this is again for Selma groups rather than assuming finiteness of Shah. Let me call it p-parity conjecture. Again over Q. Let me say most primes P. Initially he needed ordinary reduction at P, but then he, well, let's say he did most of them. Most P, so, well, okay, let me say P ordinary or potentially ordinary or multiplicative is what he could do. Kim did, again, p-parity conjecture over Q in the subsingular case. So me and Tim did parity conjecture over Q. Again, sorry, p-parity conjecture over Q. In the general case, so you had basically additive reduction cases left. But this is all over Q and for Selma groups, these last three. What we are doing is over number fields. And actually over number fields, I don't think there were any results on this.
There are some results in Nekovar's book, I think. Anyway, it doesn't matter. The point is not relevant.
So do you know which results somehow? I know he does a Q over totally real fields, definitely.
There is more than Q in his book, but I could not.
Right. Okay. Because right. Thanks.
Are there any questions? Actually, I have a question about this kind of argument. You show that there has to be points basically over a suitable extent.
Mm-hmm.
If you take an elliptic surface, even in the complex case over a curve, are there cases where you can see that geometrically? In other terms, you have the curve, you have your elliptic surface, and you make take a certain kind of covering, and then you would be able to say that you have section.
Right. So as far as I know, nobody's managed to get that to work. So for instance, if you look at this case where you have, let's say you look at all the quadratic twists of your elliptic curve, and you can try somehow to just construct a geometric family of points. Now that doesn't work, and there was even a good reason why it doesn't work. I have to remember it. Somehow the basic geometric approach, there is a good reason why it fails. Let's put it this way, but I'd have to think about it.
It's puzzling, isn't it? Because you would believe that there is some geometric analogy.
Absolutely, absolutely. So it looks like there should be something. Well, for both kind of, both when you have points or when you have this strange behavior of the rank always being even without having CM, it looks like you have some extra structure on the elliptic curve. But as far as I know, well, or rather, I don't know anything about how to construct these things.
So, I mean, this condition about the decomposition of the two torsions, or its rationality. What other, is this somehow related to any, what other phenomenon for elliptic curves kind of fall under this case where it depends on the rationality of the two torsion? The only other natural thing I can think of is the category of indecomposable vector bundles over elliptic curves. Kind of stratifies according to the rationality of the two torsion, but I don't know any other.
Well, to be honest, I haven't really thought of it, because here it was just a case of, right, we know 3 cases out of 4, let's do the last one. But I can't really say what it could be related to in some sense. Possibly if you try to do it for abelian varieties, it would become clear, but I haven't tried doing that, well, not properly, let's say. So I'm afraid I can't really give a constructive answer.
Here's a crazy, I'm sure this isn't what's going on, but if that cubic there, the cubic at the very top of the board, just the right-hand side, happened to have the property that it represented every element of k star mod k star squared, then the x-coordinate could be in the base field, and you just find. Is
well,
it
that's
likely to exist a cubic with that property? It hits every the cubic with repeated roots that hits every non-zero class of K star mod squared. A cubic over a field K of characteristics. Over a number.
I mean, I agree. It's basically an equivalent question, right?
But it's,
to,
I mean, it's
to,
not
to
quite
the quadratic
equivalent.
twist version.
Is it equivalent, actually? If you have some point, then can you use some norm trick to make the x-coordinate rational? Because you have something slightly weaker, but it wouldn't surprise me if there was just some silly trick.
No, I think if your cubic represents every element of K star mod K star square, you just
Then sure.
yeah.
But conversely, you've got the rank going up after every quadratic extension, but the new point might not have x-coordinate rational. But I'm just trying to think of a more and I'm just desperately trying to find some elementary reason why one might expect such behaviour. The rank always going up after an arbitrary quadratic extension.
Yeah.
And
If you find one, let me know.
It's the only thing that's struck. Yeah.
No, so I think with the quadratic twisting, I mean, so the rank going up is equivalent to saying that there's a point on the quadratic twist.
Yeah.
Because the rank on top is the sum of the two ranks. So basically, you just insert an extra d.
Yes. So it is the same.
So it is
the same statement.
It's just an equivalence input, but I have no idea how to do either. Though.
Yes. You're probably taking some norm.
Okay, well, thank you again.